promised that we would do today is to prove Polya theorem. So we consider a simple random walk on ZD. We define n z to be the number of n larger than 0 such that xn equals z. Okay, this is for z in ZD. And the range of x is the set of z such that n z is positive. Okay, so what's the theorem? So if d is equal to 1 and 2, then the probability that for all z in ZD and z is equal to infinity, this thing is equal to 1. Okay, so this is the first thing. Maybe I will start to use a simple P for probability, because when we consider random environment, I will use the blackboard P for the distribution of the environment. Okay, and if D is larger than 3, then the range of x is not ZD, and well, the limit when n goes to infinity of xn is equal to infinity. So this second part here, okay, it's equivalent to saying that nz is finite for every z. Okay? Because you go out of a ball after a finite time. So, right? This means that you go out of a ball after a finite time and you never come back. Okay, so what are we going to prove here? So here I'm going to modify slightly my definition. I'm going to consider n star 0, well, which is just n0 minus 1. It's just the number of visits, the number of returns to 0. Okay? And the first thing we are going to prove is that it's equivalent to say that two things are equivalent. Okay, basically, to prove that n star 0 is infinite almost surely, you just need to show that its expectation is infinite. Okay, and the reason for that is that n0 is a geometric random variable. Okay, so somehow if its expectation is infinite, it means that it's a degenerate geometric random variable, so it's equal to infinity almost surely. Okay, and then what we are going to show is that if the expectation of n0 is infinite, then not only n0 is infinite almost surely, but also nz is infinite almost surely. Okay, so this will be basically okay, okay, and then some easy part is to say that if the expectation of n0 is finite, then the expectation of nz is finite because the expectation of nz is smaller than the expectation of n0. Okay, so this gives most of the theorem, And then what we will need to do is compute the expectation of n0. Okay, I mean, or at least show whether it's finite or not. So we will show it's finite in that case, infinite in that case. Okay, and when doing this computation, yeah, somehow we would get that as a byproduct. But okay, I will not prove this fully, but I think this is not the most surprising part. Okay. So let's go. So what's the first thing we want to prove? So let me call it lemma 1. Well, it's some kind of memory-less property for n0. So the probability that the probability to make k returns to 0 okay, it's equal to the probability of making at least one return to 0 to the power k. Okay, and a corollary from that is that expectation of n0 is equal to infinity if and only if n0 is equal to infinity almost surely. Okay, so of course I wrote an equivalence here, but it's really an implication, right? Because this implication is obvious. Okay, so why is the corollary true? Well, if you look at the expectation of n0, well, this is the sum over k larger than, I think it's k larger than 1, I guess. Yes. And 0 larger than k. This is equal to the sum. So this is from the lemma. Okay, this is something general expression for the expectation. Okay, not the definition, but an easy lemma concerning the expectation. And this is the sum this geometric sum. Okay, so you have either if the expectation of n0 is equal to infinite, then the probability that n0 larger than 1 has to be equal to 1, okay, because this sum is infinite, and thus the probability that n0 is larger than k is equal to 1 for every k larger than 1. Okay, just using lemma 1 again. Okay, so is this part clear? So now to prove the lemma, basically the intuition is quite clear. Okay, what we are going to prove is that well, the probability to return at least k plus 1 times at 0, it's equal to the probability to return at least k times the probability to return at least 1 time. And well, basically we are going to look at the simple random walk at the case time, it returns to 0. Okay? And then say, okay, if I'm there, what's the conditional probability that I'm making one extra return to 0? Okay, and the idea is that what you see after k returns, because you're back to 0, it's just like a simple random walk. Okay, so the probability of making one extra return is just the same as the probability for the simple random walk to make one return. Okay, so if we had Markov chain theory to back us, this would just be the use of the strong Markov property. I'm going to do this by hand. Okay, just once, so that we get a very self-sufficient proof. So proof, okay. We will show that the probability is at n0 star. Yeah, perhaps I should put stars everywhere here. Because this thing is equal to 1 with my definition, so it's not very good. Okay, and proving things for star, it's the same as proving this. Okay, so this thing, it's equal to the probability n0 star larger than k. Probability is at n0 star is larger than 1. Okay, and basically, I'm going to prove this in a way which is does not really depend on the fact that we are dealing with a simple random walk, so that when we work with random walk in a random environment, we still have this dichotomy between recurrence and transience, and I won't have to prove things again. Okay. So I'm going to consider S1 to be the set of finite sequences. So here M is just a parameter. It's just the length of, I mean, it can be any integer. I guess it has to be larger than 1. Okay, in practice, it would be larger than 2. Okay, so it's a set of finite sequences which start from 0, end up at 0, and for all I in between, it doesn't visit 0. Okay, so well, the probability that n0 is larger than 1 is just the probability that there exists an x in S1 such that x0, x, x. Okay, and I will just use it. This is not the norm of the sequence. This is just the length of the sequence S, x. Okay, this is the M that you have here. Okay. this thing is equal to x. Okay, and now that you look at it, I mean, these events here, I mean, this is a union, okay? This is the union of over x in S1 of okay, and you can see that these events are disjoint. Okay, not two of them can be satisfied simultaneously. So because of that, this thing is just a sum over x in S1 of the probability that x0, x is equal to x. Okay. So now I'm going to define a set of paths which is such that okay, I can write basically this probability here in the same manner. Okay, and again, I think I forgot to start somewhere. Okay, so I define Sk as the set of x1, xm, m larger than 1, xm equal x0 equal 0. And what I will enforce here is that the number of i's in 1m such that xi is equal to 0, this is exactly equal to k. Okay, so this is the set of finite sequences in ZD that visit 0 exactly k times. Okay, and in the same manner, okay, well, the probability that you visit 0 at least k times, well, it's a probability that within the first steps of x, you can find such a sequence. Okay? And again, this is existent thing. I mean, it's a disjoint union of events. So you can write this as a sum. Probability that n star 0 is larger than k. It's equal to the sum over x in Sk. Probability that x1, xx is equal to x. Okay, and I mean, this thing I could write explicitly what it is, you know. Okay, so first one should restrict to nearest neighbor sequences here. And for a nearest neighbor sequence, here this probability is just 1 over 2d to the power of the length of the sequence. Okay, but I don't want to rely on the specifics of the simple random walk, so I will just not really use this fact. Okay, so now we want to use this and okay, basically we have written this as a sum, okay, and we want to show that somehow we can factorize this sum. So the first thing is to show that you can factorize the sets. Okay, so we are going to define an operation from Sk S1 to Sk plus 1, okay, which we hope to be bijective. Okay, and this operation will just be concatenation of sequences. So here, if I have x and y, I will associate to it xy, where xy, okay, is just okay. So let's say that x it's x1, xn, xm, and y it's y1, yn. Okay. Okay. X0 and y. It's y0. Okay. Then if x and y are these finite sequences, then the concatenation, it's just x0, xm, y1, yn. Okay, just put the sequences together, and I'm pulling y0. Okay, so well, this sequence starts from 0, ends up at 0, and returns to 0 exactly k plus 1 time. Okay, returns k times up to here. No visits to 0 here, and 1 visit to 0 there. Okay, so it's really it's a well-defined application, and what you have is that this application is bijective. Okay, and well, the simplest way here to see it's bijective is to construct the reverse bijection. Okay, and to construct the reverse bijection, the only thing you have to do, well, if you have okay, so this is z in sk plus 1. Okay, it starts from 0. It goes back to 0 k plus 1 times. Okay? Well, this sequence here will give me y, and this sequence here will give me x. Okay, and you can check that this is indeed the reciprocal of my operation. Okay, so x is just, well, the sequence stopped after the kth return to 0, and y is the sequence starting from the kth return to 0 and going until the end. Okay. So using this, so this is okay. Using this and this, okay, this is using this for k plus 1, okay, and this. The fact that the operation is a bijection, what you have is that the probability that n0 star is larger than k plus 1, well, this is the sum over x in sk times the sum over y in S1. Okay, instead of summing over sk plus 1, I'm summing over the Cartesian product because it's the same thing. Of the probability that x1, x0, yeah, x plus y is equal to xy. Okay, this x plus y, it's just the length of the concatenation of x and y. Note that the length, I mean, I'm not counting the 0 as part of the length. Okay? The length is not the number of terms in the sequence, it's the number of terms in the sequence starting from the next. Okay, so okay, so now to conclude, okay, I need to say that this is equal. Okay, let me write this over there. I need to say that this is equal to, well, the sum over x. Okay. Sum over y s1. I need to show that basically somehow this probability factorizes. x0, x equal x, p x0, xy equal y. Okay, so okay, why is this true? Well, this is true term by term. Okay, okay. One first reason you can argue why this is true is, well, because we know the exact expression for this. This is 1 over 2d. Okay, these things are non-zero if and only if this sequence is a nearest neighbor sequence. Okay. And in that case, this is 1 over 2d x plus y, and this is 1 over 2d x, and this is 1 over 2d y. Okay, but somehow the true reason why this is true is not because of this exact expression, but it's because if you know that you return to 0 after this number of steps, okay, then because all you perform afterwards is independent of the past, okay, just by definition of your process, basically the probabilities that the next steps are what you see next is just the probabilities that the next steps are what you see next, but starting, well, if, like, for a random walk starting at 0. Okay, so here, I'm just using, if you want, the simple Markov property and not the strong Markov property. Okay, I'm using the definition of the Markov chain, the fact that conditionally to the present, the future is independent of the past. Okay, and because the present is what I've seen at time 0, I can factorize. Okay, so this is the proof of the lemma, and somehow, okay, we will now use this trick repeatedly, and I will somehow not rewrite the details because they are exactly the same. Okay. So far so good? Okay. So now I will write a second lemma, which is the following. And I think this is so. The probability that n, okay, for yes, is it true for? Yes, it's true for n easy. all z in ZD, P of nz larger than k plus 1, it's equal to P of nz larger than 1 times P of n0 star larger than k. Okay, so let me first tell you how we are going to use this. So a consequence of that is that, well, if expectation of n0 is equal to infinity, then expectation, well, okay, what you get, yes, then expectation of nz is equal to infinity for all z in Zt. And if expectation of n0 is finite, this is always true, but then expectation of nz is smaller than expectation of n0. Okay, so basically this tells you that, yeah, if you visit n0 infinitely many times, then at least the expected number of visits to nz is infinite. Okay. And if you visit n0 finitely many times, then you also visit nz finitely many times for any z. Okay, and the way you prove the corollary, well, it's somehow immediate. The first thing is, well, just the fact that, well, the expectation of nz is equal to the sum of P nz larger than k, and k larger than 1. And that's it. Okay, so this is smaller. Okay, you get that this is equal to P nz larger than 1 times the expectation of n0. Okay, you just replace by the expectation here, and this is exactly what you get. Okay, because here, okay, if you take the star away, the k plus 1 and k plus 1 matches. Okay, so how do we prove the lemma? Well, we are going to use this path factorization. So here what we are going to do is if you want to visit the k plus 1 time, you need to visit it in 1 time. And then you need to visit it k times more. Okay, and to visit k times more, basically, well, you need to visit k, you need to return k times starting from z. But okay, here I'm not using something completely general, and when we need to amend the proof if you wanted to do something completely general, but because for the simple random walk, every vertex of ZD looks the same, okay? Visiting k times z starting from z is the same as visiting k times z 0 starting from 0. Okay, so in practice, what you can do is this. So you say that S1Z is the set of x's yes. Okay, you say that SKZ, sorry, is the set of okay, x1, xm, m larger than 1, x0 is equal to 0, xm is equal to z, and for all I in 1 n minus 1, no. The number of I in 1 m such that xi is equal to z, this is equal to k. Okay, so it's finite sequences that visit z at their last point and visit z exactly k times. Okay, and now the important thing is that, okay, maybe I should put it this way. So what we have is S1, put it in orange, S1 Z, SK, SK plus 1V. And we have to change a bit the rule of concatenation, okay? So, yes. Yeah, I don't know, whatever you prefer. You can add xm or you can add z. It's the same thing. Okay, so I'm doing a new rule for concatenating the sequences. What I'm really doing is I'm concatenating the increments, the sequence of increments. Okay, and once you have this setup, this is a bijection. Okay, just for the same reason as before, except that the picture would be more something like. Okay, this is 0, okay, and this is 0, this is z. This is the first time you touch z. This is y, and this is x. Okay, so what you do is if you start from z in this guy, you're going to stop it at the first time you visit z. Okay, okay. I have a z with an arrow and a z without arrow. Okay. So you're going to stop it at the first time you visit z. You say, okay, this finite sequence is x. And the rest, you're going to define it as y, and you're going to shift everything by z just to make it start from 0. Okay, and this is the bijection. Okay, so then you're using what we did in the previous lemma. You write the probability as a sum over paths. So okay, let me just do it for completeness. And z x in S1 Z Y in Sk S Y Z Sk and then you refactorize and you're done. Okay, so now we are almost ready to conclude. Yeah, and we need for this a last ingredient. So yeah, so far what we have proved is the following, is that if the expectation of n0 is finite, then every site is in expectation visited finitely many times. Okay, so like if the expectation of n0 is finite, there is no site which is visited infinitely many times. What we are going to show now is that if the expectation of n0 is infinite, then every z is visited infinitely many times. For all z in CD, P of nz infinite is equal to okay. And basically, this is the last thing general we are going to do, okay? That does not depend on the dimension. After that, we are just going to compute the expectation of n0 and see that it's infinite in dimension 1 and 2 and finite in dimension 3. Okay. So what's the important thing we are going to use here? Okay, we know that if this expectation is infinite, then n0 is infinite. Okay? And basically, each time, well, if you start from 0, okay, you have a positive chance of visiting z before you go back to 0. Okay? And basically, this chance of visiting z, you get it again each time you return back to 0. So basically, because you return infinitely many times to 0, you have, well, an infinite number of Bernoulli trials with the same parameter to visit z, so eventually you will succeed. Okay, so what is the proof based on? Okay, so the important thing, which is true without the assumption that you go back infinitely many times to 0. Let me check. Write this. It starts getting really messy. Okay. Okay, so let's define tau k z is the time of the nth visit of the kth visit to z. Okay, so what I claim here, and I write tau k is just tau k 0. Okay, so our claim is that the probability that tau 1z is finite. Okay, the probability, sorry, the tau 1z is small. Okay, for z non-zero, the probability that tau 1z is strictly larger than tau k, it's equal to the probability that tau 1v is strictly larger than tau 1 to the power k. Okay, the probability that you don't visit z before you return k times to 0, well, it's the probability that you don't visit z after the first return time to before the first return time to 0 to the power k. Okay, and the proof. Okay, and this time I really won't write it, but you're going to define, I don't know you're going to define Tk as the set of sequences that start from 0, or go back to 0, visit 0 exactly k times, and don't visit z. Okay, and what you have is that tau k plus 1 is in bijection with, I say t, so I will call it tk, tk times c1. Okay, and using this, you get exactly this factorization. Okay, just exactly the same thing. Basically, if you return k times, this means that at the beginning of your walk, you will see this sequence. Yeah, all sequences are mutually exclusive, so you can write everything as a sum. You can factorize stuff. I mean, we've done it already. Okay. So, yeah. So here now, the crucial thing is that yeah, this is smaller than 1. Okay? The probability that you visit z before returning to 0, it's positive. Okay, okay, this thing, it's larger than 1 over 2d to the power 2z. Okay? Just choose a path at minimal length going to z, go back. Well, this gives you this event. Okay, so it's sorry. This is smaller than 1 minus this. So this is strictly smaller than 1. So a corollary of that is that the probability that tau 1 z is strictly larger than tau k for every k larger than 1. This is equal to 0. Okay, and if n0 is equal to infinity almost surely, okay, so if the expectation of n0 is infinite because of lemma 1, then this implies that the probability that n z is larger than 1. Well, this is equal to the probability that tau 1 z is finite. Now what am I saying? Is equal to 0. Okay? Yeah. Okay, why? I mean, if n0 is equal to infinity, then all the tau k's are finite. So yeah, I mean, basically, this event is empty if n0 is finite. This is what I'm saying. But this event is just the event that you'd never visit z if n0 is infinite. Okay, and the event you never visit z has probability 0. Okay, and then I think we're good, because what we have is that the probability is that nz is larger than k plus 1, well, it's equal to the probability that nz is larger than 1 times the probability that n0 is larger than k. Okay, n0 star is larger than k. So this is equal to 1. Okay, this is equal to 1. We've just shown it. This is equal to 1. This is lemma 2, I think. No, this is lemma 1 again. Yeah. Yeah. This is lemma 2. Okay, and here we are using lemma 1. Okay, so what we have shown so far is the following dichotomy. Okay, so either the expectation of n0 is equal to infinite, and nz is finite. The probability that for all z in zd nz is finite is equal to 1, or the expectation of n0. No. And the probability equals z CD, and z is infinite, is equal to 1. So do you all agree that we have shown this so far? Okay. So the next step of the proof is to prove that we are in case A when d is larger than 3, and we are in case B when d is equal to 1 or 2. Okay, and you probably know a proof of this, but I'm going to okay, we are going to do some overkill here. So we are going to prove a little bit more than what we need, and also the way we are going to prove it is also a bit more complicated than what we need, but in order to, it's more general. So I think you might find it just interesting. Okay, so okay, what's the expectation of n0? Well, it's the expectation of the sum from n equal 1 to infinity of p x to n is equal to 0. Okay, no, sorry. This expectation of the indicator at x to n is equal to 0. Okay, so I mean, I'm just summing the indicator that you go back to 0, and I'm summing over even integers because you have no chance to go back to 0 after an odd number of steps. And if I use Fubini now, this is the sum of the probabilities that you go back to 0. Okay, so what we are going to prove now is an asymptotic equivalent for this probability. And this asymptotic equivalent is, if I'm not mistaken, 2 times square root of d over 4 pi n to the d. Okay, so in particular, okay, what you have is that when d is larger than 3, the sum of p x to n equals 0 is finite because this thing behaves like n to the minus 3/2, so it's summable. Okay, and minus d over 2, which is summable. But if d is equal to 1 or 2, this thing is infinite. So so you have case A, and here you have case B. Okay, so what's the usual proof for this? Well, in dimension 1 and 2, actually, you can get exactly this using Stirling's formula. Okay, you have an explicit expression for this, which depends on combinatorial coefficients, like binomial coefficients. Okay, in dimension 3 and more, the expression is a bit more complicated. Most of the time when you see the proof of Pauli's theorem appearing in textbooks, you only get the upper bound. Okay, you get some upper bound with some worse constant, but okay, this is sufficient here. But with some more effort, okay, you can also get this. I mean, basically using, Sweat and Stirling's formula. And this is not what we are going to do. So what we are going to do instead is to show that, well, something which is more flexible, okay? Because this is true not only for the simple random walk. Like if you have an arbitrary walk on a d-dimensional lattice, okay, this thing remains true. Okay, so it needs to be centered, and okay, we will see that what the assumptions are. I'm going to present you a more general result. This more general result will somehow not imply this, so this is a bit annoying, but we will see that you can work a little bit to make the proof give you the result you want in dimension 3. Okay, so what's, okay, and finally, perhaps, okay, something I won't delve into at all, but the advantage of what I'm doing is that also it can be used it can be used outside of the origin. Okay, so okay, why is this thing true? Why is this thing? Why do you get this n to the minus d over 2 here? Well, the idea is that after 2n step, you're typically at the distance square root of n from the origin, and you're kind of regularly distributed on that region. Okay, so the probability to be at one given point is just 1 over the volume of this ball, okay, which is n to the minus d over 2. And you can go a bit further than that. Okay, you can say that up to a constant, basically, I mean, you know that the distribution is Gaussian. Okay, and what this result kind of tells you is that this distribution is locally regular. Okay, so amongst the points that are attainable, basically, what you see locally is the density of the Gaussian. Okay, so basically, if you put here x instead of 0, and if x is attainable after 2n steps, okay, what you will get here is exactly this, but exponential minus x squared over 2n. Okay, and here you have to be a bit careful by what you mean here with the equivalent, but like this is, okay. The proof I'm going to show you, basically, with very little modification, you get the full local symmetry. Okay, so let's go. So, yeah, what are the assumptions we are working with? Okay, so I'm going to consider yi larger than 1, which is iid zd valued random variables. And I take them such that the expectation of y1 is equal to 0. And I also want, I'm also assuming that these variables are L2. So I'm assuming that this is A. And another thing is B, which is that the expectation of y1 j y1 k. So remember, these are the coordinates. Yes, all the coordinates are in L2, and the covariance matrix is sigma. Okay, and I'm assuming that sigma is invertible. Okay, so these are the first assumptions. Basically, I want that my variables to be centered and to satisfy a non-degenerate central limit theorem on RD. Okay. And now I have a third assumption, which is quite important and take some time to explain. So I don't want my variable to be okay. I want my walk to live on the full lattice. Okay, I don't want it to avoid some sites. So this is why I will need this extra assumption. So let's call nu the distribution of y1. Okay, I will call the support of nu to be the set of x's such that nu x is positive. Okay, and I will call probably a bad notation, but like I just put a bar for the symmetrized support of mu. So this is just the set of y x minus y with nu x positive and nu y positive. Okay, and what I'm going to assume is that the symmetrized support of nu generates ZD additively. Okay, so what I mean by that is for all x in ZD, there exist k, Z1, ZK in, well, there is k larger than 1, Z1, ZK in sup nu, such that Z1 plus ZK is equal to x. Okay, and yeah, I mean, here I'm taking minimal assumptions, so all of these things are necessary for the theorem to be true. And the result is the following, is that the probability, okay, I'm calling Sn is the sum from I equal 1 to n of yi. And the result is that the probability that Sn is equal to 0, this is equivalent to 1 over the square root of the determinant of sigma 1 over square root of 2 pi n to the power d. Okay, so so let me tell you why this implies our theorem in dimension 1, and why it does not imply our theorem in higher dimension. But you will see that it's not a big deal, and we can okay. In a sense, even if it doesn't imply the theorem, it clearly feels more general than this right? So if G equal 1, we can consider, yes, y1 being equal to x2. Okay, like this, like, and then Sn will just be a walk making 2 steps at a time, okay, which is kind of what we want here. In that case, what you get is, well, your sigma, which is just a scalar, so I will just write it sigma square. It's equal to, okay, what you have is that the probability is that, okay, no. Okay. Y1, I take it equal to x2 over 2. Okay? Because x2, it's an integer and it's a multiple of 2. Okay, and I want to divide by 2 just to make sure that I'm satisfying this third assumption here. Okay, so the probability is that y1 is equal to plus minus 1 is equal to 1/4, and the probability is that y1 is equal to 0, it's equal to 1/2. Okay, this is the distribution of y1. So here is my sigma square is equal to 1/2. Okay, and then you can check. I mean, you get that the probability is that x2n is equal to 0. Well, it's exactly the probability that Sn is equal to 0, and it's equivalent to 1 over square root of 1/2 1 over square root of 2 pi n to the d. And this is exactly what we want, because in dimension 1, these 2 and these 4 here, they cancel out. Well, you have no d here. And this is 1 over square root of pi n. Okay, and this is clearly overkill, because this thing is nothing more than n choose 2n, 2 to the minus n. So perhaps there was an easier way to prove this. Okay. Well, the problem is that if d is larger than 2, like this trick of dividing by 2 won't do it. Okay, because your coordinates are not all multiples of 2. It's the only thing you know that. So really, yeah, what you have is that, yeah, like if you consider, well, the best thing you can do is this, okay, and then C is not satisfied. Okay, simply because this random walk here, it lives on the half of the lattice. Okay, the lattice points whose sum of coordinates is even. Okay, and we will see how to solve this in the proof. Okay, so now I will just prove this, and in the end, I will tell you how you can adapt this to get also this result for d larger than 2. Okay. Okay, so yesterday we saw a proof of the central limit theorem, not the local one, using interpolation. But perhaps you know another proof of the central limit theorem. No? Okay, well, yeah. Does anybody know another proof of the central limit theorem? Yes, so you can use characteristic functions, meaning what you're using is Fourier analysis. Okay, you're using Fourier analysis and Levy theorem. So here what we are going to do is something similar, but we are going to use discrete Fourier analysis. Okay, which in a sense is nicer because these inversion theorems in discrete Fourier analysis are easier. Okay, so this means that we are going to, okay, this, what we are looking for is really the expectation of an indicator function. And what we are going to do is rewrite this indicator function using Fourier analysis. Okay, so what's the best way to write indicator that Sn is equal to 0? Well, you can rewrite it as, well, the integral over minus pi to the g of exponential I psi Sn d psi. And here I need to divide by 2 pi to the power d. Okay? Well, why is this true? Okay? Well, okay. If Sn is equal to 0, this is obvious. Okay, you're integrating 1 on a domain of area 2p to the power d. If Smj is non-zero for j, for some j, then what we have is that, well, the integral over minus pi of exponential I Sn j psi j g psi j is equal to 0. Okay, here I'm just integrating an exponential function. Okay, I'm just taking the kth coordinate, the j's coordinate. I'm integrating an exponential function over multiple periods. Okay, here I'm using the fact that this thing here is an integer. Okay, and this thing appears in a factor in this. Okay, because this is just a multiple integral, you can factorize it. Okay. Now, this is all good because, okay, what we have is that Psn equal to 0. Well, you can use Fubini and say, well, this is just 1 over 2d 2 pi to the power d times the integral over minus pi to the d times exponential I psi Sn, and here I have to take the expectation. Okay, so okay, here what I'm just replacing this by that and using Fubini. Okay, so now you can simplify a bit this expression because Sn is a sum of IID random variables. So the exponential is the product of a IID random variable, so you can factorize the expectation. And what you will get is just the characteristic function of y to the power n. Okay, so let me isolate this. This thing is equal to 1 over 2 pi to the power d, integral from minus pi to the d. Phi xi to the power n dxi. Very good. Okay, so now basically, okay, we are going to want to do some trick. So what we are going to need is basically the asymptotic of phi xi. Okay, you have this to the power n. So when phi xi is strictly smaller than 1 in modulus, basically this won't contribute much in the integral. So because this will decay exponentially, and even if we are tracking something that goes to 0, we are tracking something that goes down to 0 as a power. Okay, so what we need is really to control this when this is close to 1, and this is close to 1 where xi is close to the origin. Okay, so for this reason, we are going to use Taylor expansion at the origin. Okay, so what is phi xi? Well, you can do the Taylor expansion of the exponential, okay, and you are going to get that phi xi is, okay, so the first term is 1, okay. The second term is xi times the expectation of, no, it's, what is the expectation, okay, of xi y1. Okay, and the second term, it's minus 1, okay. Yeah, plus, okay, I squared 2. And then, okay, let me write this as follows. So j k equal 1 to d y1 j y1 k xi j xi k, and we take the expectation. Okay, I'm just taking the Taylor expansion, and the third term basically, well, it's going to be uniformly little o of xi to the power 3, so I can just write little o of xi to the power 3 here. Okay, so this is what we are going to use for xi small. Okay, and we can rewrite this in a simple manner because, okay, by assumption, y1 is centered. So this is equal to 0 for every xi. So what we get is really 1 minus, and this thing here, well, this is just, okay, this bracket can go there. And this is just sigma jk, so that this is just psi sigma psi divided by 2. And this is big. Okay, I'm just assuming L2, so I would. This is really what you get. Okay, so this is the estimate that we are going to use for psi small, and somehow in the remainder of the domain we need some estimate, and what we are going to show is simply the following: that if psi is larger than delta, okay, and I'm assuming that I'm in this cube. Okay, minus pi to the power g. If psi is larger than delta, then phi psi is smaller than 1 minus epsilon. Okay, for some, okay, for any positive delta, there exists a positive epsilon, so that is what. So this is for psi big. Okay, and because this thing is continuous, okay, this thing is exactly the same thing as saying, well, for all psi in minus pi to the power d, psi not equal to 0 implies phi of psi strictly smaller than 1. Okay. This is a continuous function. If it's strictly smaller than 1, away from 0, then away from a ball that contains 0, it's strictly smaller than 1 minus epsilon. Okay. Okay, and why is this true? Well, this is where we are going to use our assumption C. So what is phi of psi? Well, it's the sum of nu x exponential I psi x. Over x in ZD. Okay, so the sum of the nu x is equal to 1. Okay, so automatically you have that phi of psi is in modulus smaller than 1, smaller or equal to 1. This is just a triangle inequality. But if you want the triangle inequality to be sharp, well, you need all the terms here to have the same modulus. Okay, so this means that this is equivalent to, for all x in the support of, okay, for all x, y in the support of nu, psi x is equal to psi y. No, psi, yes. Modulo 2 pi. Okay, which is the same thing as saying for all z in the symmetrized support, psi z is equal to 0 modulo 2 pi. Okay, but now we know that this symmetrized support by assumption generates ZD. So what we have is that we can find Z1, Zk such that in the support, okay, so for all j, there exists z1, zk in the support, CU support of nu, such that, well, the sum is equal to ej. Okay, ej is just the jth vector of the base. Okay, and now what you have is that, well, z1 plus zk scalar psi, well, this is equal to psi j. Okay, and this is equal to 0 modulo 2 pi. Okay, just because, well, I can just expand this product. Okay, so therefore psi j is equal to 0. Okay, just because it lives in minus pi pi, and therefore psi is equal to 0. Okay, so what we obtained is that really, yeah, phi of psi equal to 1 implies that psi is equal to 0, which is what we wanted to prove. Okay, so what this means is that overall, okay, so this is, let me call this is 2, this is 1. Okay, if you combine 1 and 2, what you get is that phi psi is smaller than 1 minus c psi sigma psi. Yeah, yes. Okay, there exists c positive such that for all psi in minus pi pi to the power d, this is true. Okay. Yeah, I mean, you can, if psi is small, you can take this term to be at most half of this. Because, yeah, here we're using the fact that sigma is invertible. Okay, so that this is larger than the some constant times the L2 norm. Okay, yeah, let's not put sigma here. Let's put the L2 norm. This is similar. Okay, so for sigma small, you can use 1. For sigma big, you can use 2. Okay, and make just taking C sufficiently small. Okay. So now we can wrap things up, and it's going to be quick. So yeah, we want to. Okay, so the key thing is to try to get the main contribution in there, and the main contribution is going to come from, well, the values of psi for which this is roughly constant. Okay. So, well, this means that phi psi needs to be 1 minus something over n. Okay? So this means that you need this square term here to be of order 1 over n. So you mean you need the norm of psi to be of order 1 over square root of n. Okay, so because of that, we are going to do a change of variable. So the probability that Sn is equal to 0, well, this is equal to the integral on Rd. Okay, so let me, I'm taking u is equal to, I guess, square root of n times psi, right? Okay, so here I will get phi u over square root of n. To the power n. And then I get the indicator of u smaller than, yeah, u infinite, if you want, smaller then pi times square root of n, and then I get du. Okay, this is just to keep my domain of integration, and yeah, and I'm missing some terms. So let's put n to the d over 2 times p Sn equal to 0 equal 1 over 2p to the power d. Okay, I'm going to be, I want to use a, okay, so this n to the d over 2, this comes from the change of variable here. I'm just putting it on this side because now I think it's quite clear what we want to do. We are going to want to use a limit theorem here. Okay. So let's call this function here whatever we want. So let's call it fn of u. Okay, so we can say two things about fn of u. So, well, first, because of 1, we have that the limit when n goes to infinity of fn of u, it's equal to exponential minus u sigma u divided by 2. Okay, so why? Well, when n goes to infinity, eventually you won't see this indicator anymore. Okay? And so what you have is that fn of u, well, it's 1 minus 1 over n u sigma u over 2 plus little o of u square plus little o of 1 over n. Okay, this little o depends on u, but I'm just talking about pointwise convergence here, so u is fixed. Okay, to the power n. Okay, so you have 1 plus 1 over n times a constant plus something negligible to the power n. And yeah, it's okay. If everything was real, it would be really standard calculus. Well, when it's complex, okay, you have to justify it. The simplest way is to do the limits separately for the modulus and the argument if you want to come clean. But this is not something inherently difficult. Okay, so you get this, and from 2, okay, you obtain that fn of u is smaller than exponential minus c u squared. Okay, well, let me get you all the u squared over n. Okay, and here, I mean, it's really crucial in that part that you have this indicator here, because when you're using 2, yeah, you're using the indicator. Okay, and of course, it's trivially true when the indicator is equal to 0. Okay, so we're good because this thing is integrable on RD. So we can use dominated conversion theorem. Okay, so we obtain that by dominated convergence the limit when n goes to infinity of n to the g over 2 p Sn equals 0. This is equal to 1 over 2p to the power d times the integral over minus pi over rd of exponential minus u sigma u over 2 du. Okay, the fact that sigma like is positive definite, okay, it's invertible. You know that it's non-negative definite because it's a covariance matrix, and the fact that it's invertible gives you the fact that it's positive definite. Yeah, so you know that this integral is finite. This integral, okay, is actually equal to, well, okay, you get the square root of 2 pi to the d that you would get if you just had u squared here. Okay, and apart from that, you get 1 over the square root of the determinant of sigma. Okay, just think about, you have to get some determinant somewhere. And yeah, basically, if you had sigma minus 1 here, the determinant would be on top. So, okay, just think about the one-dimensional case. And yeah, if you put the sigma square on top, the sigma gets on the bottom. Okay, so yeah, so as a result, what you get is yeah, probably what we wanted, right? This simplify with this. And is this what I wrote? Yes, so this is good. Okay, so yeah, of course, all of this doesn't work. All of this doesn't work on DD just because C is not valid, and therefore this part of the reasoning does not work. Okay, so how do we change that, and how would you do if you had for instance a random walk on the hexagonal lattice or something like that, or on some transitive lattice on ZD. I don't know many of them. But, okay. So, okay, I'm not a specialist of this, so I'm going to talk about. But I think the reason is basically what I'm going to be talking about now. So. Okay, in Z2, okay, the lattice you have, the lattice of even sides, it's exactly, I mean, it's isomorphic to Z2, so it's not really a good example, but it's easier to draw. The thing that, yeah, you've changed your lattice. Okay, and all this thing with Fourier analysis, it has to do with duality. So basically, this domain of integration that you have here, okay, minus pi to the d, this somehow, I mean, like, this has to be dual to the fundamental domain of your lattice. So if you're changing your lattice, you have to change the domain of integration. Okay, and yeah, I don't know how you do this correspondence in general, but for ZD, it's not too difficult. So what we are going to consider is psi in minus pi over 2 times pi minus pi to the g minus 1. Okay, basically only half of the vertices can be attained, so we are just going to shrink the volume of the thing by 2. Okay, and this is where the factor 2 in our theorem comes from. Okay, you have factor 2 everywhere, but okay. you have. Yeah. If you remember, we had 2 times square root of 1 over 2 times 2 pi, and d here, and to the power. To the power d. So yeah, this d here is a variance term, okay, because each coordinate moves with probability 1 over d. This 2 here is also a variance term because we are taking x1 is equal to y1 is equal to x2. So we're taking 2 steps, and this 2 here is really related to the fact that we are not dividing by this by the volume 2 pi to the power d, but really it's 2 pi to the power d minus 1 times pi. Okay? So now this is out of the way. Let's do the computation. So first thing we have to check is that if, okay, so now y1 is equal to x2, okay? So if Sn, so if x2n equals 0, okay, if you want to check that the integral over minus pi over 2 times minus pi to the power d minus 1 exponential psi x2n d psi is equal to 0. Okay, so why is this true? Well, you have 2 cases. So if x2n 1 is non-zero and even, you're done. Okay? It's just because if sorry, this is what you have to do. So if the first coordinate is non-zero and even, you're done because okay, you've shrunk the domain of integration by 2, but now you're assuming that this is an even integer, so you're still integrating a trigonometric function on several periods. So you're done. If x2n1 is odd, then there exists j in 2D such that x2nj is non-zero, just because the sum of coordinates is even, and therefore you can use this factor in the integral to show that this is equal to 0. Okay, so this is the first thing we needed. Yeah, the second thing we need is to check this. Okay, where we are restricting now restricting the domain. Minus pi over 2. Pi over 2. Okay, and I'm not going to show, but it's quite obvious that now the symmetrized support of y, it really generates the lattice of even sides. Okay, this is what okay, so yeah. So now what for the triangle inequality to be sharp, I need that for all z in the support, the symmetrized support of mu, I have okay, why I have z times psi is equal to 0 to the power 2 pi. we have to conclude from there. Okay. So from there, okay, we get that 2 psi1 is equal to 0 to the power 2 pi. Okay, what I'm using this, and I'm choosing okay, so this gives me that psi1 is equal to 0. Okay, because this is psi1 equal to 0. And I think afterwards we're good, because then you take z1 plus, okay, you can put primes if you want, e1 plus ej, and this gets you that psi j is equal to 0 to the power 2 pi, to modulo 2 pi, and you're done. Okay, and the way you cut in half here, I mean, this way duality works. I mean, it's not, yeah, you can cut in half in many ways, okay? We've done it along the first coordinate, but of course you can do it along any coordinates or even in some other way, probably. These things would work. Okay, and if you just change these details in the proof, yeah, you get the proof of our local central limit theorem that you could have obtained using Stirling's formula, but I hope you enjoyed the detail somehow. Okay, any questions? Okay, so this is it for today, and on Friday we are going to start to study the one-dimensional random walk in a random environment.